Our second type of interference is probably the most straightforward of the three: spectral interference. This is when an analyte signal is coincident with a different atom signal. Analyte signal is coincident with a different atom signal. For example, if we were to study a sample of lithium, we would find that it absorbs a different combination of wavelengths than calcium. But we would also observe that one of the wavelengths that lithium happens to absorb is almost the same as a wavelength that calcium absorbs. And if we were detecting this particular wavelength of light for our calcium analysis, and our unknown happened to have some lithium in it, well, then lithium's going to absorb that light too, and that's going to affect our signal, like so. Example: if Li is in unknown with calcium, because again, that unknown has other chemicals in it. In this case, what's going to happen is calcium is going to absorb light at 610.27 nanometers. That is its peak absorption for that yellow wavelength that's highlighted above. And so we know a peak is going to have some width to it. And then lithium is going to absorb almost the same wavelength at its peak. And let's say there's enough lithium so that its maximum intensity is here, and its wavelength is 610.33. But again, that peak has some width to it, so it is going to overlap with our calcium peak. So calcium's here, lithium's here. As far as that instrument's concerned, this is what the spectrum looks like. It's just going to combine all of that absorbance into like one rather strange looking peak. And let's say that the 610.27 nanometers is right here, which again is what we're tracking for the calcium. And we can see that because of that lithium infiltration, this intensity is higher than it should have been if we had just had calcium by itself. And so our signal goes up. Signal increases. And with that in mind, let's walk through the effects on our analysis. What if you measured the absorbance of 610.27 nanometer light and lithium was present in the unknown? First, we draw the representation of what should happen. Here's our calibration curve, and here's our unknown being plugged in and solved for, and let's say everything here represents the truth. Now we ask ourselves our three questions to see how we deviate from that truth. Question 1. Which sample experiences the interference? In this case, it's the unknown that's going to experience spectral interference. 2. How does that interference change the measured signal? Well, we just covered that. It increases the signal. 3. What is the consequence on the calculated unknown concentration? Well, if our absorbance just went up, and it's being plugged into the correct calibration curve, then our measurement will go up as well. And so that's an example of how spectral interference can mess with our analysis. So now quickly think for yourself, how could we fix this problem? Well, the simplest thing to do is to just pick a different wavelength to detect, right? We see calcium absorbs different wavelengths of light, not just that yellow one, and most of these other wavelengths don't coincide with the wavelengths that lithium absorbs, right? So our signal might be weaker, but as long as it's strong enough that we can make reliable measurements, it's okay. So here's what we'll write. Fix. Pick a different wavelength to study. Pick a different wavelength to study. And in parentheses, we'll note that the signal might be weaker, but that's okay. Signal might be weaker, but that's okay. Next, I'll tack on a clicker. This one we're just going to do in Zoom. I'll just point out that it highlights that in this particular example, lithium can ultimately have two different effects on our signal. So it's not always this simple cut and dry scenario where only one thing can possibly change by the presence of some other chemical. But we'll do this later. And we'll also cover the third interference in the next lecture.